From the moment human beings first gazed upward at the night sky, a silent wonder has filled the mind. Countless points of light shimmer across the heavens, each a star burning across vast stretches of time and distance. To our ancestors, the stars seemed eternal, glowing without change or end. Yet science has revealed a truth both humbling and profound. Nothing in the cosmos is permanent. Stars are born, they age, and eventually they die. Galaxies form, drift, and collide. Even the very fabric of space itself is not fixed, but stretches and evolves. If everything within the universe has a beginning and an end, then does the universe itself share that same destiny? It is perhaps the most inevitable of all questions. If we accept that the universe has a history, with a starting point known as the Big Bang, then we must also accept the possibility of a conclusion. To ask when and how the universe might end is not simply a poetic curiosity. It is a scientific inquiry, as urgent and serious as asking where it all began. Just as cosmologists spend their lives studying the light from the earliest galaxies, they also look far ahead, running the clock of cosmic physics forward to glimpse the final chapter of everything. The universe is not static. It is a story still being written, and every story, by definition, has an ending. The history of cosmology is in many ways the history of this question. For millennia, philosophers debated whether the universe was eternal or finite. Aristotle believed the cosmos had always existed and always would. Ancient Indian thinkers imagined endless cycles of creation and destruction, like breaths of a cosmic being. It was only in the 20th century that astronomers, aided by telescopes and mathematics, discovered compelling evidence that the universe had a birth. The discovery that galaxies are moving away from one another at immense speeds, revealed by Edwin Hubble in 1929, proved that the universe is expanding. This expansion implies a beginning in the distant past, some 14 billion years ago. If the universe could be born, then logically, it might also someday die. What controls this ultimate fate are the same forces that govern its evolution today. The tug of gravity, the energy of matter, the mysterious push of dark energy, and the geometry of space-time itself. The universe is like a great balance, with mass and energy pulling inward, and expansion, driven by space itself, pulling outward. Whether the universe will collapse, freeze, tear apart, or fade into silence depends entirely on this delicate cosmic equation. Scientists use the concept of critical density, the precise amount of matter and energy needed to halt expansion after infinite time. If the universe holds more than that amount, gravity could eventually overcome expansion and pull everything back together. If less, expansion will continue forever. Yet even this balance is complicated by the discovery of dark energy, a strange and invisible form of energy that appears to be driving the universe to expand faster over time. The more deeply cosmologists investigate, the less certain the answers become. Different measurements of the universe's expansion rate disagree with one another, creating what is known as the Hubble constant tension. Some methods suggest one value, while other methods suggest another. This discrepancy means our models may still be missing an important piece of the puzzle. Dark energy, too, remains one of the greatest mysteries in all of physics. Is it a property of space itself, a kind of vacuum energy that never changes? Or is it something dynamic, evolving with time, perhaps destined to strengthen or weaken in the far future? Without knowing its true nature, predictions about the universe's fate remain educated guesses, like tracing the outline of a shadow without seeing the object that casts it. Still, the search continues because the stakes are nothing less than cosmic. To ask how the universe will end is to confront the scale of time beyond human comprehension. We live for decades, civilizations endure for centuries, stars burn for billions of years, yet the fate of the universe unfolds on scales that dwarf even these spans. Trillions of years into the future, all stars like our sun will be gone. Quintillions of years later, even black holes may evaporate. To contemplate the end is to step outside human time entirely, into the deep time of physics itself. Why does this question matter to us? Fragile beings on a small planet circling an ordinary star, perhaps because it reflects our deepest fears and hopes. We know our own lives are finite, that everything we love will someday pass away. The universe feels like the one eternal stage on which the human drama is performed. To learn that the universe itself may also have an end is to recognize that impermanence is not merely a human condition, but a cosmic truth. It connects us to the fabric of reality in a profound way. Science and philosophy converge here. For some, the idea that the universe will one day fade into silence is terrifying, as though meaning itself will vanish. For others, it is liberating, reminding us that the value of life is not in how long it lasts, but in the wonder it inspires while it is here. Cosmology does not diminish mystery, it enlarges it. Every measurement of the sky, every equation of expansion, every observation of distant galaxies carries within it a reminder that the cosmos is both knowable and unknowable, precise in its laws, yet infinite in its implications. To peer into the end of the universe is to gaze into a mirror of our own mortality, yet it is also to discover resilience, for even if the universe ends, it does so according to laws that are majestic, lawful, and beautiful. Whether in silence or in fire, in collapse or in endless expansion, the universe will not ask for permission. It will simply continue the story written into its very nature. And so the inevitable question becomes a journey. To imagine the end of the universe, we must understand how it has evolved so far, from its birth in a primordial fire to the galaxies and stars that light our skies today. The end cannot be seen without first knowing the steps along the way. The story of cosmic destiny begins with the life and death of stars, the engines of creation that shape galaxies, worlds, and life itself. The story of the universe is not written in sudden leaps, but in slow unfolding, across ages that make human history seem like the blink of an eye. To understand where the universe is going, we must retrace the path it has taken, guided by the principles of physics that hold true across all of time. When Hubble discovered the expansion of the universe, it was not only an observation of galaxies moving away, it was a revelation that the very stage of existence, space itself, was stretching. The further away a galaxy lies, the faster it appears to recede. This is not because it is traveling through space like a ship crossing an ocean, but because the ocean itself is expanding beneath it. The universe is not a container holding galaxies. It is the fabric that connects them all, and it is that fabric which is changing. Expansion means the universe was smaller in the past. If we turn back the cosmic clock, galaxies draw closer, matter grows denser, temperatures rise. The picture culminates some 14 billion years ago, in an event we call the Big Bang. It was not an explosion in space, but the sudden appearance of space and time themselves in a state of unimaginable density and heat. Out of that beginning emerged everything we see today, from atoms to galaxies. The Big Bang gave the universe a clear point of origin, but once that door was opened, another question followed with certainty. If the universe began, then how will it end? The answer depends on how the expansion behaves. Imagine throwing a stone upward into the air. If your throw is weak, gravity pulls the stone back down. If your throw is just strong enough, the stone rises and then eventually falls. But if your throw is powerful enough, the stone will escape Earth's pull and travel into space forever. The universe is like that stone. Gravity from all the matter inside it tries to pull everything back together, while expansion pushes outward. For decades, cosmologists debated whether gravity would be strong enough to halt expansion, leading to a collapse, or whether expansion would continue endlessly, cooling and thinning the cosmos. Then came a surprise in the late 1990s. Observations of distant supernovae, exploding stars that serve as cosmic mile markers, revealed that the expansion of the universe is not slowing down as expected. It is speeding up. Something unseen, something we now call dark energy, is accelerating the expansion. This discovery transformed cosmology. It implied that not only will the universe not collapse, but it might stretch itself apart at an ever-increasing rate. Dark energy remains one of the deepest mysteries in science. We know it exists because we see its effect on cosmic expansion, yet we do not know what it island. Some scientists believe it is a property of the vacuum of space itself, a constant energy that fills every region of the cosmos. Others suggest it could be a dynamic field, one that changes over time. The future of the universe hinges on which of these possibilities is true. If dark energy is constant, the universe may slowly drift toward a cold and empty state. If it strengthens with time, it could eventually rip apart galaxies, stars, planets, and even atoms. Cosmology therefore becomes not only the study of the past, but of possible futures. Each equation written on a chalkboard, each telescope trained on a distant supernova, Each refinement in the measurement of the cosmic microwave background radiation is part of a collective effort to sketch the outlines of fate. Yet the answers remain elusive. Even today, different methods of measuring the expansion rate produce different results. Some approaches suggest the universe is expanding faster than others predict. This disagreement, called the Hubble constant tension, may be a clue that our understanding is incomplete. These uncertainties are not weaknesses, but reminders of the vastness of what remains to be discovered. They are the gaps in the map that invite exploration. Humanity has only just begun to measure the universe with precision, and the questions we face now may someday be answered with clarity we can hardly imagine. But even then, the profound question will remain: why does the universe end at all? Why is impermanence written into its very structure? The human mind naturally resists the idea of endings. We long for permanence, for something unchanging that gives meaning to everything else. Yet nature teaches us otherwise. Stars live and die. Mountains rise and erode. Even atoms decay over immense times. To imagine the end of the universe is to accept that impermanence is not an exception but the rule. The cosmos itself follows this law. What end it chooses is not a matter of preference or design, but of physical inevitability. There is a strange comfort in this. If the universe ends in silence, in collapse, or in fire, it does so according to rules that are impartial and universal. The same equations that describe an apple falling from a tree describe the arc of galaxies across billions of years. To glimpse the end of the universe is to see not tragedy, but inevitability, not despair, but the grandeur of natural law. And yet, to humans, the idea remains personal. For when we ask about the end of the universe, we are also asking about our place within it. We know our species will not endure for eternity, nor will our planet, nor even our star. But to wonder about the fate of the cosmos is to extend our imagination beyond ourselves, to see our lives against the backdrop of time so vast it can barely be spoken. It is an act of humility and of awe. So the inevitable question stands at the threshold of science and philosophy alike. The universe has a beginning. Does it also have an end? To pursue this question, we must follow the path of cosmic evolution, to see how the universe has changed and will change across the aeons. The first step on this journey lies in the lives of stars, the luminous engines of matter and light that give the cosmos its brilliance. They are the architects of worlds and the destroyers of them. To understand how the universe might fade, we must first understand how stars themselves live and die. The question of endings lingers like a shadow over every discovery. Each new observation of the heavens sharpens the picture, yet also reminds us of the limits of knowledge. We have traced the expansion of galaxies, measured the radiation left over from the Big Bang, and catalogued the distribution of matter across cosmic webs of unimaginable scale. These triumphs in understanding carry us further, yet the inevitable question always returns. If the universe began, must it not also conclude? To search for the end is to step into a realm where human imagination struggles to keep pace. Numbers describing time become so large that language itself bends under their weight. 1 billion years is already beyond our lived experience. 1 trillion years is 1,000 times greater still, and yet the universe may endure for spans of time far greater than that. Cosmologists speak of epochs so vast that stars burn out, galaxies dim, and even the most massive black holes vanish. To most minds, these intervals are abstractions, yet they are the natural flow of cosmic time. The end of the universe will not come in a moment we could ever witness, but will unfold in stages, spread thinly across eternity. The very act of asking about the end connects the human story with the cosmic one. Our ancestors who painted stars onto cave walls were reaching for the same answers. What is the nature of the sky? Where did it come from? Where will it go? Today, armed with physics, we can describe expansion, entropy, and dark energy. Yet the essence of the question remains unchanged. It is a yearning to understand whether the universe is a cycle or a line, whether it breathes in endless rhythms of creation and destruction, or whether it drifts toward a final silence that will never be broken. There is a haunting beauty in this pursuit. The laws of physics are precise, but the destiny they describe is vast and poetic. If the universe fades into heat death, it will be a story of slow dwindling, of stars burning their last fuel, of galaxies scattering into the dark. If it collapses, it will be a tale of fiery return, of matter rushing back into a singular point of unimaginable density. If dark energy grows without limit, it may be a violent story, with every structure ripped apart until even atoms dissolve. If quantum physics allows a vacuum decay, then the end may arrive suddenly, without warning, rewriting the laws of reality in a heartbeat. Each possibility carries a different rhythm, yet each arises from the same pursuit of truth. The fact that we cannot yet choose among these endings is not failure, but an invitation. It shows us that the universe still holds secrets greater than our knowledge. To live in an age where the cosmos is expanding, where stars still shine, where life can reflect on itself, is to live in a brief and precious chapter. Someday, aeons from now, the universe may be dark and empty. But now, in this rare moment, it is luminous and full of questions. That alone is enough to give meaning. Philosophers may ask whether an ending diminishes value. If the universe is destined to fade, does that make existence less significant? Yet perhaps it is the opposite. Endings remind us that every instant matters more because it is fleeting. The grandeur of a star is not diminished by the fact that it will one day die. Its light is beautiful precisely because it will not last forever. In the same way, the knowledge that the universe itself has an end adds weight to our contemplation. We are not wandering aimlessly in eternity. We are part of a story with a beginning, a middle, and an end. And so the inevitable question is not only a scientific puzzle, but also a mirror held up to ourselves. We ask how the universe will end, but in truth, we are also asking how we endure endings in our own lives. Death, loss, change, impermanence. These are not just cosmic laws, but human ones. To see them written into the stars is to see our own reflection on a grand scale. The universe will end without our consent, without our intervention, and without concern for our survival. Yet while it lasts, it offers us the gift of wonder. The fact that we can imagine its fate, calculate its expansion, and speculate about its destiny is itself extraordinary. We are creatures made of stardust, asking the stars about their own mortality. Few questions could be more poetic or more inevitable. And so the journey continues. To glimpse the end, we must first study the engines that power the cosmos today. Stars, those blazing furnaces of light and creation, are the key. They shape galaxies, forge elements, and determine the character of the universe across vast epochs. To understand the future of the universe, we must begin with the lives and deaths of stars. Only then can we trace the path toward the greater ends that await. Stars are the luminous engines of the cosmos, the great furnaces that transform simple elements into the complexity that makes life possible. For billions of years, they have lit the universe, scattered heavy elements into space, and given galaxies their brilliance. Yet even these giants of fire are not eternal. Like living beings, stars are born, they live, and they die. Their deaths mark not only the end of their own existence, but also the beginning of new possibilities. For it is in their violent endings that the universe is enriched with the ingredients of planets and people. To understand the fate of the universe, we must begin with the fate of stars. For the end of starlight is the first true step into cosmic darkness. Our own sun is a modest star, middle-aged and stable, burning hydrogen into helium in its core through nuclear fusion. This delicate balance between the inward pull of gravity and the outward pressure of fusion has allowed it to shine for more than 4 billion years. But this balance cannot last forever. In roughly 5 billion years, the sun will exhaust the hydrogen in its core. When that fuel is gone, gravity will take hold and the core will contract, growing hotter and denser. The outer layers will expand outward, swallowing the inner planets, possibly including Earth, as the sun becomes a red giant. In this swollen state, the sun will glow with a deep crimson light, hundreds of times larger than it is today. For a time, the sun will burn helium into carbon and oxygen, but this too will eventually end. With no more fuel to sustain nuclear fusion, the sun will shed its outer layers into space, creating a glowing shell of gas called a planetary nebula. At the center, all that will remain is a dense white dwarf, a stellar ember no larger than Earth, but with a mass nearly equal to the Sunday. White dwarfs no longer burn fuel. They shine only from residual heat, slowly cooling over billions upon billions of years until they fade into cold, dark remnants, sometimes called black dwarfs. Though none yet exist in the universe, since the cosmos is not old enough for white dwarfs to have cooled completely, they are the final destiny of stars, like our Sunday. But not all stars live such quiet lives. Some are far more massive, burning brighter and shorter, like cosmic fireworks. A star many times more massive than the Sun will burn its fuel quickly, its core reaching temperatures where heavier elements are forged: carbon, oxygen, neon, silicon, all the way up to iron. Yet iron is the end of the road for fusion, for it cannot release energy by being fused. When the core of a massive star fills with iron, it becomes unstable. Gravity, unchecked, causes the core to collapse in a fraction of a second. The outer layers slam inward, rebound, and are blasted outward in a titanic explosion known as a supernova. Supernovae are among the most violent events in the cosmos, outshining entire galaxies for brief moments. In their fury, they scatter heavy elements into space, seeding the cosmos with the ingredients for planets, oceans, and living beings. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were born in the death throes of massive stars. It is a strange truth that we are the children of stellar deaths, assembled from the ashes of long-gone suns. What remains after a supernova depends on the mass of the star's core. If the core is modest, perhaps 1.5 times the mass of the Sun, it collapses into a neutron star, a city-sized object of almost incomprehensible density. A teaspoon of neutron star material would weigh billions of tons. If the core is heavier still, no known force can halt gravity, and it collapses into a black hole, a region of space where gravity is so strong that not even light can escape. These stellar corpses, neutron stars and black holes, linger in the galaxy as the lasting testimony of once brilliant suns. The universe is full of such remnants. Billions of white dwarfs silently cool in the darkness. Millions of neutron stars spin like cosmic lighthouses, their magnetic fields beaming radiation across space. Countless black holes lurk invisibly, revealed only by their gravitational pull on nearby matter. Together they form the graveyard of stars, a reminder that even the most radiant sources of light must someday fall into shadow. The death of stars is not just an astronomical fact, but the beginning of the universe's long night. For as stars age and fade, galaxies lose their brilliance. The Milky Way, which now glitters with hundreds of billions of stars, will one day dim as new star formation slows and eventually ceases. Hydrogen, the raw fuel for new stars, will become scarce. The universe will move into an era when existing stars burn out one by one and no new stars are born to replace them. Over trillions of years, the galaxies will grow darker until only the corpses of stars remain. This is the first glimpse of the cosmic end, the transition from a universe of blazing starlight to one of fading embers. The deaths of stars set the stage for all that follows, for once their light goes out, the universe begins its slow descent into darkness. As the aeons roll forward, the drama of stellar life and death unfolds on timescales that dwarf human imagination. Our own sun, destined for its transformation into a red giant and eventual white dwarf, is but one player in an endless cosmic cycle. Across the galaxy, stars are born within vast clouds of gas and dust, igniting into brilliance and eventually collapsing into remnants that will either cool silently or explode violently. Each star follows its own script, written by its mass, yet all end with the same inevitability. Consider again the red giant phase of the Sunday. As it swells, it will cast off its outer layers, enriching the interstellar medium with elements forged during its lifetime. These drifting shells of gas will shimmer for a brief cosmic moment as a planetary nebula, then fade into invisibility. What lingers is a white dwarf, no longer a furnace, but a cooling ember. Over trillions of years, it will radiate its heat into space until it becomes so cold and dim that it merges into the blackness around it. These so-called black dwarfs, though hypothetical now, are the final grave markers of stars like ours. The fate of massive stars is far more spectacular, though just as inevitable. Their rapid lives burn through fuel at astonishing rates, sometimes lasting only a few million years compared to the Sun's 10 billion-year lifespan. When such stars die in supernovae, they alter not only their own surroundings, but the entire evolution of galaxies. Shockwaves from these explosions trigger new star formation in nearby clouds. Heavy elements scattered across space collect into new planetary systems. Life itself owes its existence to such fiery deaths. In the end, destruction becomes creation, and the cycle continues. Among the remnants of these explosions are neutron stars. Imagine a sphere only 20 kilometers across, containing more mass than the Sunday. The matter inside is compressed so tightly that protons and electrons merge into neutrons, creating a fluid of nuclear density. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep across space like a lighthouse. These pulsars, as they are known, were first detected in the 1960s. At first, mistaken for signals from extraterrestrial intelligence because of their uncanny regularity. Yet they are simply the clocks of the cosmos, ticking with a precision born from the collapse of stars. Even more extreme are stellar black holes. When a massive star's core collapses with no force strong enough to stop it, space-time itself gives way. A singularity forms, hidden behind an event horizon from which nothing can return. To fall into a black hole is to cross a threshold where gravity becomes absolute. These remnants, invisible, yet powerful, drift silently through galaxies. They can be detected when they draw in matter from companion stars, heating it into glowing disks of X-rays, or when their gravity bends the light of distant objects. In their presence, we glimpse the most profound extremes of physics, where space and time are warped beyond ordinary understanding. Galaxies themselves are shaped by the deaths of stars. The Milky Way is filled with regions where supernova remnants have spread shockwaves across interstellar clouds, stirring turbulence that compresses gas into new generations of stars. Yet this process is finite. Over trillions of years, the raw material for star formation will be consumed. Each new star is a temporary flame lit from a dwindling supply of hydrogen. Eventually, the balance tips, and no more stars can form. From that point on, the universe will only grow darker. In that distant future, the night sky will look very different from what we know today. The bright constellations familiar to us will fade as their stars die. Red dwarfs, the smallest and longest-lived stars, will dominate the final era of starlight. These faint stars can burn their hydrogen for trillions of years, far longer than stars like the Sunday, but even they will not endure forever. In time, they too will exhaust their fuel, swelling briefly before collapsing into white dwarfs. The last star to shine may be a small red dwarf countless trillions of years from now, flickering its final light into a universe already deep in shadow. When the last star fades, the universe will cross a threshold. No more light will be born from nuclear fusion. The cosmos will enter what astronomers call the degenerate era, dominated not by luminous stars, but by the remnants of what once was. White dwarfs, neutron stars, and black holes will populate the darkened galaxies. Their presence will be silent, cold, and enduring. The universe, once filled with brilliance, will have taken its first irreversible step toward its eventual end. To contemplate this future is to imagine a universe in mourning. The blazing splendor we now take for granted is temporary, a brief golden age in the cosmic timeline. Someday, the stars will be gone, and with them, the light that defines our nights. Yet, even in their deaths, stars shape the destiny of all that follows. They determine the structure of galaxies, the chemistry of planets, and the possibilities for life. To understand the universe's end, we must accept that the death of stars is not only the end of light, but also the gateway to the next great chapter. As the universe drifts deeper into the ages of time, the death of stars becomes not a rare spectacle, but the dominant theme. Galaxies, once vibrant with stellar nurseries, will slowly exhaust the raw fuel that births new suns. Already, in our own Milky Way, star formation has declined compared to its peak billions of years ago. The glittering spiral arms that today blaze with blue newborn stars will one day quiet, their brilliance replaced with the fading glow of older and dying ones. The universe will become a graveyard of stellar remnants, each telling the silent story of a long-extinguished flame. Imagine wandering the cosmos in this distant future. Where once the sky was a river of starlight, it will grow dim and sparse. White dwarfs will be scattered across space, each a cooling ember of a star that once shone. Neutron stars will continue their silent spin, perhaps still emitting beams of radiation, though ever more faint. Black holes will lurk unseen, swallowing matter that strays too close. The sky will no longer be alive with birth and death in equal measure. It will lean only toward decline, toward the gradual extinguishing of all things bright. Among the last stars to endure will be the red dwarfs. These are the smallest and most common stars in the universe, too faint to be visible to the naked human eye, but far more numerous than larger stars. They live with extraordinary thrift, consuming their hydrogen so slowly that some will shine for trillions of years. If we think of the universe as a theater, red dwarfs are the longest-lasting actors on the stage, carrying the light long after the giants have fallen silent. But their longevity is not immortality. Eventually, they too will exhaust their fuel. When that day comes, even the final red glow will fade. In this twilight era, strange processes may keep the cosmos from total darkness, though only briefly. White dwarfs may occasionally flare back to life in nova explosions if they gather material from companions. Collisions between remnants may ignite bursts of energy. Yet these are accidents, rare flickers in an otherwise fading universe. Over time, even these sparks will cease, leaving only silence and shadow. The transformation from a universe of stars to one of remnants marks a profound shift in cosmic history. For billions of years, starlight has been the great sculptor, driving chemistry, forging heavy elements, illuminating galaxies, and making life possible. Without stars, the universe loses not only its brilliance but also its creative engine. The pathways of new worlds and new life will close. The universe will still exist, but it will be a colder and lonelier place. A theater without actors, a stage where the curtain has quietly fallen. Yet the end of stars does not mean the end of cosmic drama. What remains after their deaths will continue to evolve. White dwarfs will cool into invisible black dwarfs, slowly radiating their last heat. Neutron stars, dense beyond comprehension, may collide to create bursts of energy even in this darkened age, scattering elements like gold and platinum into the void. Black holes will continue to merge and grow, their gravity shaping the silent structure of galaxies. The universe, after the death of stars, is not lifeless, but its changes occur in shadows, subtle and inexorable. On these timescales, the human imagination falters. Trillions of years is a number so vast that it empties into abstraction. Yet physics gives us the power to trace even these stretches, to follow the laws of thermodynamics and gravitation into futures far beyond our own. The death of stars is not speculation but certainty, written into the equations of fusion and gravity. To witness the stars today is to see them mid-story, glowing in the brief era when the cosmos is still alight. And so we return to the inevitable theme: nothing endures forever. Stars, which seem to us the most permanent fixtures of the sky, are temporary flames. Their brilliance is the exception, not the rule. The natural state of the universe is darkness, punctuated by rare and finite bursts of light. Once those bursts fade, the universe will slip into shadow. This is the first great ending we encounter, the death of starlight. But the universe does not stop with stars. Their remnants will lead to the next act of cosmic destiny. As galaxies fade, black holes will dominate. These dark giants, born from stellar deaths and fed by galaxies themselves, will become the most powerful and enduring objects in the cosmos. To understand the next chapter in the story of endings, we must follow the path beyond stars into the reign of black holes. The age of starlight is only a fleeting act in the long play of the cosmos. When the last stars fade, the universe does not fall silent at once. A new era begins, one ruled by the most mysterious and powerful remnants of all, the black holes. These are not merely the corpses of massive stars. They are the gravitational titans of the universe, capable of swallowing suns, reshaping galaxies and bending space-time itself into unfathomable curves. In the darkness that follows the death of stars, black holes will stand as the final monuments of cosmic grandeur. Every galaxy we see today hides a supermassive black hole at its center. The Milky Way harbors one known as Sagittarius A, a dark colossus with a mass 4 million times that of the Sun. Some galaxies contain central black holes billions of times the Sun's mass. The origin of these monsters remains a mystery. Did they grow from the collapse of the first giant stars, or did they form directly from enormous clouds of gas in the infant universe? However they were born, their presence dominates galactic life. In their youth, these black holes devour matter with insatiable hunger, forming blazing accretion disks that outshine their entire host galaxies. These quasars, brilliant beacons visible across cosmic distances, are among the most luminous objects ever observed. As the galaxies age, star formation dwindles, and so does the feast that fuels the central black holes. Yet even as the cosmic banquet ends, the black holes remain, silent and enduring. They are patient entities. Time does not erode them as it does stars. Their event horizons remain stable, swallowing whatever dares to cross. Stellar black holes, born from supernovae, roam the galaxies like predators, capturing companion stars or tearing apart unlucky wanderers. The supermassive ones at the centers remain like lords of silence, exerting their influence across millions of light years. The universe in the black hole era will be a strange place. Imagine galaxies stripped of light, their stars long extinguished, leaving behind only remnants. In their darkness, black holes will continue to merge. When galaxies collide, so too will their central black holes, spiraling inward until they fuse into a larger whole. Each merger releases a storm of gravitational waves, ripples in space-time itself, that radiate outward at the speed of light. Though faint, these waves carry the signatures of cataclysm, the echoes of structures collapsing into one. Over trillions of years, this process will create fewer but ever larger black holes, until supermassive giants dominate the silent remnants of galaxies. Yet even black holes are not eternal. In the 1970s, Stephen Hawking revealed that the quantum nature of space-time means black holes slowly leak energy in the form of radiation. This Hawking radiation is unimaginably weak for large black holes, far beyond the reach of any observation today, but across timescales so vast that the words themselves strain, the effect becomes decisive. Over 10 to the power of 67 years, a black hole with the mass of the Sun would evaporate entirely. The largest black holes, those with billions of solar masses, might endure for 10 to the power of 100 years. But even they cannot last forever. The black hole era will therefore not be a final age but a transition. One by one, black holes will radiate their energy back into the universe. At first, the evaporation will be slow, imperceptible, but as the mass shrinks, the process accelerates, ending in a final burst of radiation, a brief flare before the black hole vanishes completely. What was once the most indomitable structure of gravity will dissolve into the faint whisper of particles scattered into space. To us, living in the age of stars, black holes seem like eternal prisons from which nothing escapes. Yet physics insists they are only temporary. Their dominion over the universe is long, but not infinite. When they are gone, the cosmos will be stripped even of these last titans, leaving only a thin haze of particles drifting in the cold. Still, the black hole era will last longer than everything that came before it combined. Compared to this, the age of stars is a brief prologue. For aeons upon aeons, black holes will reign over a silent and darkened cosmos, merging, devouring, waiting. They are the keepers of time itself, standing watch over a universe sliding into entropy. In their shadows, the story of endings takes on its most profound shape. The death of stars is a tragedy of light. The black hole era is a tragedy of gravity. And beyond even this lies a future stranger still, a universe drained of energy, sliding toward its ultimate fate. The silence of black holes will give way to something even colder, even darker. The cosmos will drift toward heat death, the stillness of maximum entropy, where nothing new can ever occur. To follow the end, we must leave behind even the black holes and step into the final silence. The rule of black holes is a reign measured in unthinkable spans of time. To human beings, even 1 billion years is incomprehensible, yet black holes will endure for periods that make billions seem like brief sparks. In this long era, galaxies will drift ever farther apart due to cosmic expansion, yet within each island of gravity, black holes will remain the most significant inhabitants. The stars are gone, but these dense wells of gravity still bend the fate of everything that remains. Across trillions of years, black holes will grow, not by steady feeding, but by rare encounters. Rogue stars, wandering too close, will be torn apart in catastrophic displays of tidal destruction. Clouds of gas, stripped from galaxies long past their prime, will spiral inward and vanish beyond the event horizon. When galaxies merge, as they often do, their central black holes will dance around each other in colossal orbits, radiating gravitational waves until they collapse together. Each such merger gives birth to an even more massive black hole, forging cosmic monarchs that dominate the ruins of galactic empires. For most of their lives, however, black holes are quiet. They do not glow or shine. They reveal themselves only by their influence, the way they warp the paths of nearby stars or bend light from objects behind them. In the darkened universe to come, even these signs will fade. With fewer stars to betray their presence, black holes will drift like invisible phantoms, unlit and unyielding. They will be the last sources of drama in a cosmos grown still. The greatest of them, the supermassive black holes at galactic centers, will reach unimaginable sizes. Some may grow to trillions of times the mass of the Sun, absorbing stars, remnants, and other black holes. In this future, black holes will be the architects of what little structure remains. They will define the centers of dark galaxies, exerting their pull on whatever material lingers nearby. Their collisions will send tremors through space-time, ripples spreading outward forever in the silence of the void. Yet even as they reign, a quiet process is at work that will undo them. Hawking radiation, the ghostly quantum whisper at the edge of the event horizon, ensures that black holes are not eternal. This effect is negligible on human timescales. A black hole of stellar mass will take 10 to the power of 67 years to evaporate. The largest black holes, with billions of solar masses, will take closer to 10 to the power of 100 years. These numbers stretch beyond any analogy. If the current age of the universe were a single heartbeat, the lifespan of black holes would be an ocean of centuries layered upon centuries. Yet physics leaves no doubt. Given enough time, they too will vanish. The end of a black hole is not a quiet disappearance. As it shrinks, its radiation grows more intense. In the final instant, the black hole releases an immense burst of energy, far outshining anything else in its surroundings. For a moment, the darkness is broken by this last flare, the final breath of an object that has endured longer than any star. Then it is gone, leaving behind only radiation and particles diffused into the emptiness. This cycle will repeat until every black hole in the universe has dissolved. The cosmos, once filled with billions of galaxies alive with stars, will be reduced to a thin mist of radiation and the faint drift of subatomic particles. The black hole era will end, and with it the last chapter of cosmic structures. All that will remain is the slow slide toward equilibrium, the final approach to maximum entropy. There is a strange poetry in this fate. Black holes, which seem to us eternal, are revealed as temporary. Their gravity is absolute, their darkness total. Yet the laws of quantum mechanics insist that nothing, not even a black hole, can endure forever. The balance between the largest and smallest scales of physics writes an ending that neither relativity nor quantum theory alone could have predicted. In this meeting of extremes lies one of the deepest truths we know about the universe. To live in the age of stars is to see the cosmos in its youth. To imagine the age of black holes is to look into its old age, when the universe has grown quiet and patient. Beyond that lies a fate colder still, when even the black holes are gone and nothing remains but silence. It is toward that silence that the cosmos is heading, step by step, over distances of time that stretch imagination to breaking. Even as we trace these endings, there is a sense of awe that cannot be diminished. The black hole era reminds us that the universe is not static. It evolves, it changes, and it confronts us with the truth that everything ends. What comes after black holes is the final act of cosmic entropy, a story of dwindling energy and the extinguishing of possibility. That story, known as heat death, is where our journey next must lead. The age of black holes stretches out so far ahead that human imagination falters. When stars are gone and galaxies are no more than silent collections of remnants, black holes will continue to reign for aeons upon aeons. They will merge into ever larger giants, consume what matter still drifts nearby, and then wait in silence while time itself unfurls. Their event horizons will cast shadows across eternity, invisible yet absolute. But gravity alone cannot guard them forever. At the edges of their horizons, quantum processes whisper. Hawking showed that black holes are not perfectly black. Instead, pairs of virtual particles flicker into existence from the quantum foam of space-time. Normally, these pairs annihilate one another instantly. Near the event horizon, however, one particle may fall inward while the other escapes. To a distant observer, the escaping particle is real, a faint radiation leaking from the black hole. Over inconceivably long spans of time, this process drains the black hole of energy, reducing its mass. The pace of this evaporation is slower than anything we can measure today. A black hole with the mass of the Sun would take 10 to the power of 67 years to vanish. Larger ones would endure even longer. For the titans at the centers of galaxies, with billions of solar masses, lifetimes stretch toward 10 to the power of 100 years. These are spans so vast that even words collapse into abstraction. Yet they are finite. The law is clear. Eventually, even the greatest black holes must end. As evaporation nears its final stages, the process accelerates. Radiation intensifies. The black hole shrinks rapidly, and at the very last instant, it releases a burst of energy in a final explosion. For a moment, the cosmos will see flashes of light, like sparks dying from a great fire. Then those sparks, too, will fade, leaving only cold emptiness where once giants ruled. This will mark the close of the black hole era, a chapter of cosmic history that lasted longer than all others combined. The universe, which once blazed with starlight and then was shaped by gravity's titans, will become a place without luminous structures, without furnaces of fusion, without gravitational monarchs. All that remains will be the diffuse haze of particles and low-energy radiation scattered thinly across expanding space. The story told by black holes is one of paradoxes. They are born in the most violent stellar deaths, yet they outlive the stars themselves. They are objects of immense gravity, yet they slowly dissolve through the faintest of quantum processes. They seem eternal, yet they are temporary. Their existence reveals the deep harmony between relativity and quantum mechanics, two pillars of physics that often seem in conflict. In the behavior of black holes, the universe whispers of a unity not yet fully understood. When the last black hole fades, the universe will enter its final silence. With no stars and no remnants, only particles drifting endlessly, the cosmos will be as close as possible to equilibrium. Energy will be spread so thin that nothing new can form, no structures can arise, no complexity can survive. It will be a universe of stillness, where the arrow of time itself has no direction, because there are no changes left to mark its passage. This is the vision known as heat death, the ultimate end of everything we know. From the brilliance of stars to the silence of black holes, the cosmos will finally collapse, not in fire, but in emptiness. To imagine such an end is to look into the heart of entropy, the relentless drift of the universe toward disorder and balance. It is the fate that arises not from violence but from inevitability, the natural conclusion of laws that have guided the universe from its birth. The black hole era, then, is not only a chapter of endings, but also a bridge to the final act. Once the last gravitational giants vanish, the cosmos will be left to entropy alone. Darkness will not be the result of collapse or tearing, but of slow dispersal, of the quiet expansion into silence. This is where our journey next must lead, into the cold embrace of the heat death of the universe. The universe, once a stage ablaze with stars and galaxies, drifts toward a future that is colder and quieter than anything we can now imagine. After the era of black holes has ended, when even the greatest gravitational titans have evaporated into nothingness, the cosmos enters its final act. This is the age of heat death, the silent march toward maximum entropy, where the universe becomes uniform, empty, and still. No explosions, no collapses, no grand spectacle will mark this fate. Instead, it arrives slowly, inevitably, like the cooling embers of a fire that has long since burned out. Entropy is the measure of disorder, the tally of how energy is spread out. In the beginning, the universe was hot, dense, and filled with structure, waiting to be built. Over time, gravity gathered matter into galaxies, stars, and planets, creating pockets of low entropy where order could flourish. These structures burned with energy, drove complexity, and even gave rise to life. Yet with every process, entropy increased, energy dispersed, and the universe moved closer to equilibrium. Heat death is the final stage of that process, when energy is spread so evenly across the cosmos that no differences remain, no gradients exist to drive motion, and no possibility of change endures. To understand this fate, picture a room filled with air. If all the air is compressed in one corner, it can expand, doing work. But if the air is spread evenly throughout the room, nothing more can happen. The system is in equilibrium. The universe is like that room, only unimaginably larger. Galaxies, stars, and black holes represent compressed pockets of order, capable of releasing energy and creating structure. But as time marches forward, those pockets fade. In the end, the cosmos is like a room already filled with evenly spread air. There is nowhere left to expand, nothing left to do. This is not a death in the sense of destruction. It is a death of possibility. In a heat-death universe, no stars shine, no planets orbit, no black holes lurk. Only a thin haze of photons, neutrinos, and elementary particles drift through expanding space. The temperature of this universe approaches absolute zero, though never quite reaching it, hovering forever near emptiness. There is no motion, because there are no gradients of energy to sustain it. It is not silence after noise, but silence eternal, with no potential for sound to ever rise again. The timescales involved stretch beyond imagination. Black holes take 10 to the power of 100 years to evaporate. Beyond that, heat death extends into times so vast they defy words. It is the final horizon of physics, where all change has ceased. Some cosmologists describe it as the ultimate equilibrium, a cosmic graveyard where time itself loses meaning. Without events, without differences, there is no way to mark the passage of time. The universe does not end in a bang, nor in a collapse, but in an endless twilight where nothing ever happens again. And yet, this fate is not without its strange beauty. The grandeur of heat death lies in its inevitability. It is the logical consequence of the second law of thermodynamics, a principle so universal that it governs both the melting of ice and the death of stars. It is a reminder that the universe is consistent, that the same laws shaping a candle's flame also shape the destiny of galaxies. The poetry of physics is that the largest and smallest scales obey the same truths, and from that truth arises the stillness of the end. For those who wonder about meaning, heat death poses profound questions. Does a universe that ends in silence make everything before it futile? Or does it mean that value lies in the fleeting brilliance, the temporary existence of stars and life that emerge in the brief window between chaos and equilibrium? In this view, the end does not erase the beauty of what came before. It frames it. A flower is no less beautiful because it withers. A star is no less magnificent because it dies. The universe, too, is no less wondrous because it will someday fall quiet. The concept of heat death also forces us to reconsider time itself. In our daily lives, time is marked by change, by clocks ticking, planets orbiting, and hearts beating. But in the stillness of heat, death, none of these exist. Without change, time loses meaning. The universe would persist, yet, in a sense, it would no longer have a story. It would simply be unchanging, a canvas with no painter and no picture. The path toward this fate is inexorable, but not unique. Physics allows other possibilities, other endings shaped by gravity, dark energy, or quantum instability. Heat death is perhaps the most serene, a slow fading rather than a violent collapse. It is a vision of the cosmos dissolving into uniformity, a quiet end that respects the symmetry of natural law. But just beyond this silence lie alternatives that are anything but peaceful. Before we accept heat death as the final word, we must explore the other doors the universe may yet walk through. In the long view of eternity, heat death is a kind of stillness that grows so gradually it is almost imperceptible. Long before the final silence, the universe will already appear dark and desolate to any observer. The last stars will flicker out, leaving behind only remnants. White dwarfs will cool into invisible black dwarfs. Neutron stars, those dense city-sized relics, will radiate their final faint heat. Black holes, having devoured whatever matter wandered close, will evaporate slowly, their final sparks vanishing into emptiness. Step by step, the sources of energy will dwindle until none remain. Entropy is not only a scientific principle, but a story of loss. In our everyday world, it is why hot coffee cools, why order gives way to disorder, why every system tends toward equilibrium. On the grandest stage, entropy rules the cosmos. It tells us that energy, though conserved, can become useless, spread too evenly to do work. This is the destiny of the universe in the heat-death scenario. The brilliance of stars and the drama of galaxies are temporary patterns etched against the backdrop of entropy's rise. At first glance, heat death seems abstract, almost unreal. What does it mean for the universe to run out of usable energy? Imagine a world where every battery is drained, every flame extinguished, every river stilled. Machines cannot run because there is no difference in energy to power them. Life cannot endure because there is no warmth, no light, no chemistry. Scale that vision to the universe, and you glimpse what lies ahead. A cosmos where particles still exist but do nothing, drifting in eternal equilibrium. Some cosmologists call this the Big Freeze, for the temperature of the universe will fall closer and closer to absolute zero. Yet it is not a freeze in the sense of ice, but rather a thinning, a dilution of energy until nothing stirs. The expansion of space ensures this outcome. As galaxies move ever farther apart, their contents grow isolated. Eventually, observers in any surviving galaxy remnant would see nothing beyond their local horizon. Even if intelligence survived to this distant epoch, it would find itself trapped in solitude, with no evidence that other galaxies had ever existed. Memory itself would become impossible, for there would be no way to preserve records when every system decays and no energy remains to sustain them. There is, however, a certain inevitability to this future that resonates with elegance. Heat death is not random destruction, but the expression of natural law. It is the end written into the second law of thermodynamics, the same law that governs the cooling of stars and the decay of order in everyday life. If the cosmos truly ends in this way, it will not be because of catastrophe, but because of balance. All gradients erased, all possibilities exhausted, the universe will achieve a perfect uniformity that can no longer evolve. The timescales are staggering. After the black hole era, after 10 to the power of 100 years, the universe may still continue expanding for unimaginable stretches. The heat death scenario does not mark a single moment, but an asymptote, a long approach to equilibrium that never truly completes. Even after quadrillions of years, traces of particles may still move, but the differences between them will be meaningless. End quote. End quote. End of 4. Unquote. The cosmos will persist, but without change, without events, without the possibility of anything new. From a human perspective, this vision is haunting. We live in a universe of light and motion, where stars rise, planets orbit, and life flourishes. To imagine all of that fading into silence feels like the extinguishing of meaning itself. Yet, it is precisely because the universe is temporary that its brilliance is precious. The glow of stars, the spark of life, the presence of thought, all of these exist against the vast backdrop of entropy. Their rarity makes them miraculous. There are philosophers who argue that heat death is not an end but a transformation. If the universe is a story, then perhaps its final chapter is not about loss, but about completion. A system that has reached maximum entropy has reached its conclusion, not in tragedy, but in inevitability. The universe began in a state of low entropy, filled with potential. It ends in high entropy, potential spent. The arc between is the story of everything: galaxies, stars, life, and thought. Heat death is the closing of that arc. And yet, for all its inevitability, heat death is not the only ending imagined by cosmology. It is the most serene, but others are more violent. Some scenarios predict collapse. Others predict tearing apart. Still, others suggest sudden quantum catastrophe. Before we settle into the stillness of heat death, we must confront these alternatives, each one a possible destiny written into the laws of physics. The universe may not fade gently, it may end with fire. The vision of heat death is unsettling, not because it is explosive or catastrophic, but because it is so quiet. In the farthest stretches of time, when the last sparks of black holes have faded, what remains is a universe that has lost its power to change. Energy will still exist, but it will be spread so evenly that no work can be done. No new structures can form. No stars can ignite. It is a cosmos stripped of all contrast, a vast sea where every ripple has smoothed away. To live in such a universe would be impossible, not merely because life needs energy, but because meaning itself relies on difference. A clock can only tick if something changes. A memory can only form if there is a before and after. In heat death, there is no before and after. The arrow of time, which has always been driven by entropy, loses its direction when entropy is complete. The universe does not end with an event. It simply becomes a state, unchanging, endless, and still. This strange fate carries a kind of poetry. The cosmos began in fire, in a hot, dense state where energy was concentrated and gradients were immense. Out of that imbalance arose galaxies, stars, planets, and life. Over billions of years, those gradients have been consumed. Energy has flowed from hot to cold, from ordered to disordered, driving the story of creation and destruction. Heat death is simply the conclusion of that story, the point where imbalance is gone. The fire burns down not in a flash, but in the slow exhaustion of all fuel. Even in this silence, the laws of physics still hold. Particles will continue to drift, photons will continue to expand with space, and the universe itself will continue to grow. But these motions will be empty of drama. No galaxies will form, no stars will shine, no planets will orbit. The cosmos will have reached its final equilibrium, not destroyed, but exhausted. It will not be a death marked by collapse, but a death marked by permanence. For us, fragile beings who measure time in years and centuries, such a future seems remote beyond comprehension. Yet, the inevitability of entropy is already visible all around. Stars exhaust their fuel. Machines wear down. Energy flows toward disorder. On the largest scale, the same principle applies. To witness the brilliance of the night sky is to witness temporary beauty, for every star is a brief flame against the march of entropy. Heat death reminds us that the cosmos we know is young, caught in a brief luminous chapter before the silence of eternity. And still, some question whether heat death is truly inevitable. The nature of dark energy, which drives the acceleration of cosmic expansion, remains uncertain. If dark energy behaves differently over time, the universe's fate may shift dramatically. Perhaps gravity will someday overcome expansion, reversing it in a catastrophic collapse. Perhaps dark energy will grow stronger, tearing apart galaxies, stars, and even atoms in a violent Big Rip. Or perhaps a quantum instability could trigger vacuum decay, rewriting the fabric of physics itself in an instant. Heat death is serene, but alternatives lie waiting, hidden in the equations. Yet even among these possibilities, heat death retains its haunting appeal. It is not violent, but absolute. It reflects the deepest law of thermodynamics, the principle that underlies every process from a falling stone to a burning star. It tells us that the universe is consistent, that the same rules apply from beginning to end. In its silence lies a strange comfort, the knowledge that nothing is arbitrary, that the cosmos unfolds as it must. For human beings, contemplating heat death is less about predicting the future than about understanding the present. To know that everything ends makes what exists now precious. The warmth of the sun, the glow of the stars, the fragile spark of life on a small blue planet, all are temporary, and therefore, all are invaluable. The universe does not need to last forever to be meaningful. Its meaning is in the fact that it exists at all, in the fleeting brilliance between beginning and end. Thus, the chapter of heat death does not close the book but opens a door. It shows us one possible horizon, a vision of eternity in stillness. But the universe may not choose this path. Other endings remain possible, shaped by forces we do not yet fully understand. To glimpse these alternatives, we must returning to the fire from which it was born. The stillness of heat death is not the only destiny that has ever been imagined for the cosmos. For much of the 20th century, many astronomers believed that gravity, the great sculptor of stars and galaxies, might one day reclaim its throne and bring the universe back to where it began. This vision is known as the Big Crunch, a future not of silence and fading light, but of collapse and fire. Instead of expanding forever, the universe would eventually slow, halt, and reverse, pulling everything back inward until all matter and energy, once again, converge in a singular state. It is the mirror of the Big Bang, a cosmic symmetry where the end resembles the beginning. The idea arises naturally from the struggle between expansion and gravity. The Big Bang set the universe in motion, galaxies racing apart from one another, like sparks from an explosion. Yet gravity, though weakened by distance, never sleeps. Every galaxy pulls on every other. Every particle exerts its influence. If the universe contains enough matter, if the combined weight of galaxies, stars, dark matter, and everything else exceeds a certain critical threshold, then gravity could someday halt the expansion. Like a stone thrown upward that slows, pauses, and falls back down, the universe itself could reach a turning point. From that moment onward, contraction would begin, pulling all things closer and closer. In this scenario, the night sky would change in ways unimaginable to us. Galaxies that once drifted apart would begin to approach. The great cosmic web of matter would tighten, threads of gravity drawing together into knots. Stars and galaxies would collide more frequently as the fabric of space itself shrinks. Temperatures would rise as matter compresses. Black holes would merge in a frenzy of violence. The once cold and expanding universe would become hotter, denser, and brighter as everything rushes together. As contraction accelerates, the universe would become a furnace. Radiation, trapped in the shrinking cosmos, would heat everything. The distances between galaxies would vanish, and the great structures of the cosmos would dissolve into a uniform fireball. At the final moment, all matter and energy would be crushed into a singularity, a point of infinite density and temperature, much like the state from which the universe was born. The Big Crunch is, in essence, a return to the beginning, a closing of the cosmic circle. For some, this vision carries a strange sense of balance. The universe begins with a bang, expands for a time, then collapses into a crunch, only to perhaps be reborn again. It suggests a cycle, a cosmic heartbeat of creation and destruction. Philosophers and scientists alike have been drawn to the elegance of this possibility, for it frames the universe not as a linear story with a beginning and an end, but as a rhythm, that repeats across eternity. The Big Crunch, however, depends critically on the density of the universe. For decades, astronomers sought to measure how much matter the cosmos contains. Galaxies and stars provided only part of the answer. Dark matter, invisible but detectable through its gravitational pull, added much more. Yet even when combined, matter and dark matter seemed to fall short of the critical density needed for a collapse. Then came the discovery of dark energy, the mysterious force driving accelerated expansion. With dark energy in the equation, the possibility of a crunch grew dimmer still. Expansion is not slowing, it is speeding up. This does not mean the Big Crunch is impossible, but it means it requires assumptions about dark energy that differ from what we now observe. If dark energy changes over time, if its strength diminishes or reverses, gravity might once again take the lead. In that case, the universe could still halt and collapse, though the timeline would stretch into unimaginable aeons. Much depends on the true nature of dark energy, a mystery we have not yet solved. The vision of the Big Crunch is more than scientific speculation. It is also a reflection of our longing for cycles, for the comfort of return. Many cultures have imagined worlds that rise and fall, die and are reborn. The Big Crunch offers a cosmic echo of those myths, suggesting that even if everything ends, it may also begin again. For some, this possibility is less bleak than heat, death, for it means that the universe does not drift into silence, but continues in an eternal rhythm. Yet whether it is real or not remains uncertain. The evidence we have today suggests expansion will not stop, but accelerate. Still, the Big Crunch remains an important chapter in our exploration of endings. It shows us that gravity is not only the force that shapes galaxies and stars, but also a contender for the final fate of everything. To imagine the cosmos collapsing back into fire is to confront the power of gravity at its most absolute, a reminder that the universe may not end in silence, but in a storm that returns us to the beginning. As the idea of the Big Crunch unfolds, the universe becomes a place where endings are not final silences but violent returns. Imagine billions of galaxies that once drifted farther apart, now reversing course. The sky would grow crowded as cosmic structures, once separated by millions of light years, begin to converge. Over unimaginable spans of time, galaxy after galaxy would collide, merging into larger and larger systems. The night would no longer be dark and sparse, but filled with blazing light from collisions, tidal streams, and the fury of matter set ablaze by compression. The physics of such a universe would be extraordinary. As contraction progresses, radiation that once thinned out across expanding space would be squeezed together again. Photons, the carriers of light, would grow more energetic as the scale of the universe shrinks. What was once cold cosmic microwave background radiation would warm, regaining brilliance. The cosmos would be reborn as a furnace, heated not by nuclear fusion in stars but by the very act of collapse. Entropy, which always increases, would not reverse, but its flow would be guided into ever higher temperatures and densities. The difference is that instead of fading into uniformity, the universe would end in compression, in fire. Stars and stellar remnants would not survive such a collapse. White dwarfs, neutron stars, and black holes might endure for a time, but as contraction tightens, even they would be swept into mergers. Supermassive black holes at the centers of galaxies would drift closer, their orbits decaying as gravitational waves carry away energy. Eventually, they would collide, fusing into even greater monsters. In the final stages of contraction, the cosmos might be dominated by a handful of titanic black holes, circling each other in a shrinking arena of space-time. Their collisions would shake the fabric of the universe, but with no space left to radiate into, their violence would fold into the approaching singularity. The end of the Big Crunch is almost unimaginable. As distances shrink towards zero, temperatures rise toward infinity. Matter cannot remain in its familiar forms. Atoms are torn apart, nuclei smashed, quarks themselves pressed into an undifferentiated state. Gravity becomes irresistible, not only pulling matter together, but crushing space-time itself into collapse. In the final instant, everything that exists returns to a point of infinite density, a singularity like that which once marked the beginning. Does this singularity mean true annihilation, or could it mark a new beginning? This question has fascinated both physicists and philosophers. Some theories suggest that the universe could rebound, a new expansion emerging from the collapse. This would make the Big Crunch not an end, but a transition, a doorway to another Big Bang. If so, the cosmos may be cyclic, an eternal heartbeat of creation and destruction. Others suggest the singularity may be the end of time itself, a boundary beyond which no physics can describe or predict. In that case, the Big Crunch would be final, an irreversible collapse with no sequel. Evidence today leans against this fate, for the expansion of the universe is accelerating rather than slowing. Dark energy appears to push galaxies apart ever more quickly, not allowing gravity to pull them back. Yet, science thrives on uncertainties, and dark energy is not fully understood. If it evolves with time, changing its nature, the cosmic story could yet alter. The Big Crunch remains a valid possibility, a scenario that lingers at the edge of cosmology's imagination. For human beings, the Big Crunch carries emotional weight. It is easier to accept than heat death for some, because it promises return rather than endless silence. A universe that collapses back into a singularity could be a universe that gives birth again, repeating cycles without end. This echoes ancient traditions, from Hindu cosmology to Stoic philosophy, where the cosmos breathes in and out, dies, and is reborn. Whether science confirms it or not, the idea satisfies a deep longing for cycles, for the comfort of recurrence. Yet science demands evidence, and for now the evidence points elsewhere. The accelerating expansion we observe suggests that the universe will not fall back on itself, but stretch into emptiness. Still, the Big Crunch remains a powerful vision, a reminder that the laws of gravity hold within them not only the power to create, but also the power to end. To imagine the cosmos collapsing back into a fireball is to confront gravity at its most absolute, a force that can shape not just worlds and stars, but the destiny of the universe itself. If the Big Crunch does mark the end, then perhaps it also marks the beginning of something new, a cycle beyond our comprehension. But if not, the universe may still find other endings. For just as collapse is possible, so too is rebirth without final silence. From the ashes of a crunch may rise the possibility of a bounce, a universe that breathes again. The Big Crunch draws its strength not only from mathematics but from the profound human intuition that endings and beginnings are often bound together. If the universe collapses into a singularity, might that collapse ignite a new expansion? This question transforms the Big Crunch from a vision of final destruction into one of potential renewal, a cosmic phoenix rising from its own ashes. In this way, the end of everything could also be the beginning of everything once again. As contraction progresses, the cosmos would become a place unlike anything we know. Galaxies, once vast cities of stars, would compress until they are indistinguishable. The boundaries between structures would dissolve as everything falls inward. In those final moments, the density of matter would be so great that no familiar forms could survive. Atoms would collapse, nuclei would break apart, and the basic building blocks of matter would merge into an undifferentiated soup of fundamental particles. Temperatures would soar beyond the heart of any star, beyond even the conditions of the earliest Big Bang, until all matter is reduced to extremes that defy our current physics. Time itself may seem to rush toward a boundary. With every contraction, events grow more intense, more compressed, until the distinction between past, present, and future blurs. At the singularity, time as we know it may cease altogether, the dimensions of space collapsing into a point where physics offers no description. For some, this is a true end, a curtain beyond which nothing can be said. For others, it is a threshold, a door into the unknown, where new physics may reveal that singularities are not endings, but gateways. The possibility of a rebirth from the Big Crunch is tantalizing. In some models of quantum cosmology, the singularity could bounce, triggering a new expansion filled with fresh energy and structure. If this were true, our universe could be one cycle in an infinite series, each Big Bang giving rise to galaxies, stars, and life. Each Big Crunch drawing everything back to begin again. In such a picture, eternity is not silence but rhythm, a cosmic breath that never ends. Yet this vision must contend with the reality of entropy. In each cycle, entropy increases. If the universe were truly cyclic, then with every repetition the amount of usable energy would diminish, and the cosmos would grow ever more disordered. Eventually, the cycles might fade, leaving heat death as the final horizon after all. But perhaps new physics, not yet discovered, could reset entropy with each bounce, allowing true cycles to continue without end. These questions remain unanswered, resting at the frontier of theory. What we know today suggests that the Big Crunch is unlikely. The acceleration of cosmic expansion, driven by dark energy, points toward a future of continued growth rather than collapse. But science is cautious, for dark energy itself is mysterious. We do not yet know if it is constant, or if it will weaken or reverse over time. If it changes, the balance of forces could shift, and gravity might one day dominate again. The universe could still turn inward, collapsing into fire. The Big Crunch, then, remains both a scientific hypothesis and a philosophical metaphor. It is the image of return, of the universe folding back into itself, of beginnings and endings as one. Even if evidence leans elsewhere, the idea endures because it captures something timeless in human thought. We imagine circles and cycles because they reflect the patterns of life and death we know. Stars are born and die, seasons return, generations rise and fall. The Big Crunch magnifies these rhythms to the scale of the cosmos. If the universe does collapse, the ending will be violent and final, yet also strangely familiar, echoing its beginning. If it does not, then the Big Crunch will remain a vision, a story told by gravity that we can only imagine. Either way, the idea has shaped how we think about the cosmos. It shows us that endings may not always be endings alone, that sometimes the greatest destruction may hide the seeds of creation. And so, from the fiery vision of the Big Crunch, we turn to another possibility, that collapse is not final, but part of a cycle, a universe that contracts and expands endlessly. This is the vision of the Big Bounce, a cosmos that does not die, but breathes eternally. The Big Crunch paints a picture of a universe collapsing into fire, perhaps to end, perhaps to begin again. Out of that possibility arises a more radical idea, one that suggests the universe has never truly had a single beginning, nor will it ever have a final end. This vision is called the Big Bounce, and it imagines the cosmos as eternal, cycling endlessly through expansion and contraction, death and rebirth. Instead of a line with a start and a finish, the universe becomes a rhythm, a heartbeat, echoing across infinite time. The notion of a bouncing universe is not new. Ancient cultures dreamed of cosmic cycles, worlds born and destroyed in eternal return. In modern physics, the Big Bounce emerges from attempts to solve the riddle of the singularity at the heart of the Big Bang. According to classical relativity, the universe began in a point of infinite density, a place where our equations break down. But quantum theories of gravity suggest that singularities may not exist. Instead, when matter is compressed to extremes, new laws may appear, halting collapse and triggering a rebound. The singularity becomes not an end, but a turning point. Imagine the universe in contraction. Galaxies rush together, stars collide, and matter is crushed into densities beyond imagination. Yet instead of collapsing into a singularity, quantum effects resist further compression. Space-time itself becomes elastic. Just as a ball bounces when squeezed against the ground, the universe rebounds when pushed to its limits. A new expansion begins, filled with energy and potential. What we call the Big Bang may in fact have been the rebound of a previous universe collapsing in its own crunch. In this picture, our universe is not the first, and it will not be the last. Countless universes may have come before, each one living, dying, and reborn in an endless sequence. The galaxies we see, the stars we admire, even the existence of life itself may be part of an infinite chain of cycles. each arising from the ashes of the one before. The arrow of time, so central to our experience, may be just one phase in an eternal dance. The Big Bounce has appeal because it avoids the problem of the beginning. If the universe had a Big Bang, what came before? Classical cosmology offers no answer, for time itself began with the bang. But in a bouncing model, the bang was not the beginning, only the latest rebound. There is no first moment, only an endless series of moments. Eternity stretches both backward and forward. The universe has always been and will always be. The science behind the Big Bounce lies in the frontier of physics, in the effort to merge general relativity with quantum mechanics. Theories such as loop quantum gravity suggest that space-time itself has a discrete structure, like a fabric, woven from finite threads. At extreme densities, this fabric resists collapse, creating pressure that leads to a bounce. Other models, drawn from string theory and brane cosmology, propose that our universe might be one of many membranes in higher dimensions, colliding and rebounding to create cycles of Big Bangs. These ideas remain speculative, but they offer a profound alternative to final endings. Instead of drifting into silence or collapsing forever, the universe breathes. Expansion gives way to contraction, contraction to expansion, forever. The cosmos is eternal, not because it avoids death, but because death itself is only a passage to rebirth. For us, this vision is strangely comforting. It suggests that nothing is final, that endings are beginnings in disguise. The death of stars, the collapse of galaxies, even the crunch of a universe are not tragedies, but transformations. The cosmos does not vanish, it renews. In the Big Bounce, destruction and creation are inseparable, two halves of one rhythm. And yet, even this elegant vision must contend with the mystery of dark energy. For the universe today is not contracting, but accelerating in its expansion. If that acceleration continues without change, contraction will never begin, and the bounce will remain only a dream. To know whether the universe truly bounces, we must understand dark energy, the invisible hand that now guides its fate. Until then, the Big Bounce remains a possibility, a vision of eternity that waits at the edge of physics. The idea of the Big Bounce reshapes not only how we think about the future, but also how we think about the past. If the Big Bang was not the beginning, but only the latest rebound, then what we call the origin of the universe was a transition, not a birth. The light of the cosmic microwave background, the distribution of galaxies, even the laws of physics themselves, could be echoes from cycles that came before. In this vision, the universe carries scars of its past incarnations, like rings in the trunk of a tree or ripples spreading across a pond. Some models of the bounce suggest that traces of earlier universes might linger in subtle ways. Perhaps the large-scale structure of galaxies carries imprints of previous cycles. Perhaps tiny anomalies in the cosmic microwave background radiation are whispers from before the bang. If such evidence exists, it would be faint, buried in noise, nearly impossible to detect. Yet the very possibility suggests that our cosmos may not be unique, but part of a sequence stretching infinitely in both directions of time. The elegance of the Big Bounce lies in its ability to replace singularity with continuity. In classical cosmology, the singularity at the start of the Big Bang is a boundary where physics breaks down. Equations explode, predictions fail, and we can say nothing about what lies before. But if the universe bounces, there is no singularity. Physics remains valid, and the chain of cause and effect extends beyond the bang. The mystery of origins is softened, transformed from an absolute beginning into a cycle without end. In this way, the Big Bounce resonates with deep philosophical traditions. The idea of cycles is ancient, found in myths from India, Greece, and beyond. The Hindu concept of kalpas imagines the universe created and destroyed in endless repetition. The Stoics envisioned cosmic conflagrations, followed by rebirths. In the Big Bounce, modern physics converges with these ancient intuitions, suggesting that the universe itself may share the rhythm of cycles we see in nature, from seasons to lives to civilizations. But the Big Bounce is not only philosophy, it is a serious scientific hypothesis born from the struggle to unify quantum mechanics and general relativity. In loop quantum gravity, for example, space is not continuous, but granular, made of finite loops woven together. At extreme densities, these loops resist further compression, creating a repulsive force that prevents a singularity. Instead of collapsing into nothing, the universe rebounds. In string theory and brane cosmology, collisions between higher dimensional surfaces can trigger repeated expansions, each one experienced as a Big Bang in our universe. Though different in detail, these models share the idea that collapse is not an end, but a transition. Still, challenges remain. Entropy always increases, even in a bouncing universe. With every cycle, disorder should accumulate, making each new expansion less ordered than the last. If the cycles are truly infinite, why do we see such low entropy at the start of our universe? Some theorists propose mechanisms that reset entropy at each bounce, perhaps through quantum effects or the physics of higher dimensions. Others suggest that cycles are not eternal but finite, with a beginning after all. The debate continues, and the answers remain uncertain. What is certain is that the Big Bounce offers an alternative to the final stillness of heat death. Instead of fading into silence, the universe may live forever, pulsing with an eternal heartbeat. To us, caught in one cycle, this is nearly impossible to grasp. Yet it is a vision of hope, a reminder that endings may not always be final, that even the collapse of everything may be only a doorway to something new. For humanity, this possibility resonates deeply. We see cycles all around us. Day follows night, seasons follow one another, lives begin and end while new lives are born. To imagine the cosmos itself sharing this rhythm is to see our existence mirrored on the largest scale. Perhaps the universe, like us, does not vanish, but transforms, returning again and again in endless renewal. And yet, the fate of the bounce depends on the one mystery we cannot yet solve: dark energy. The force driving today's accelerated expansion may prevent contraction altogether. If its strength remains constant or grows, the universe will never return to collapse. Expansion will continue without end, and the dream of a bounce will be denied. But if dark energy changes, if it fades or reverses, the cosmos could still turn inward, leading to the possibility of rebirth. Until we know the truth of dark energy, the future remains open. As the story of the Big Bounce reaches its conclusion, the universe emerges not as a single event, but as an eternal process. In this vision, the cosmos has no true beginning and no true end. Instead, it is a rhythm, a pulse that beats across the expanse of infinite time. Each cycle of expansion and contraction carries with it the seeds of the next, like a breath that draws in and releases without ever stopping. In the contraction phase, the universe would gather itself, galaxies collapsing inward, temperatures rising, matter pressed into extremes. This would be a time of violence and transformation. When black holes merge, stars are torn apart, and space-time itself bends toward compression. Yet, as densities climb toward what classical relativity calls a singularity, quantum effects may intervene, halting the collapse before infinity is reached. The very structure of space-time resists annihilation, and in that resistance lies renewal. The contraction does not end in destruction, but in reversal, a bounce that ignites a new expansion. If this is true, the Big Bang we know is not the first, and it will not be the last. Countless universes may have existed before ours, each one with its own galaxies, its own stars, its own stories. When one collapses, another is born. Our existence, then, is not the product of a unique creation, but a single chapter in an eternal series. The thought is humbling and immense. It means that the universe is infinite, not only in space, but in time. A cosmos without borders in either direction. Yet the Big Bounce is not free of paradox. Entropy, the measure of disorder, always increases. In each cycle, disorder should accumulate, making every new universe less ordered than the one before. If the cycles are endless, why does our universe begin in such a state of low entropy, rich with potential for structure and complexity? Some theories propose that the bounce itself resets entropy, scrubbing the slate clean with each rebound. Others suggest that entropy may be carried into hidden dimensions or transformed in ways we do not yet understand. The problem remains unsolved, a frontier where physics meets mystery. For now, the evidence does not favor the bounce. Observations show that the universe is expanding faster and faster, driven by dark energy. If this acceleration continues, contraction will never begin, and the dream of a cyclical cosmos will fade. But dark energy itself is a riddle. We do not know if it is constant or if it will change in strength over time. Should it weaken or reverse, contraction could still occur, and the bounce could still be real. Until we understand dark energy, the question remains open. Even if the Big Bounce is not the ultimate truth, its vision shapes how we think about existence. It shows us that beginnings and endings may be illusions, that what we call the birth of the universe may be only a transformation. It resonates with the cycles we see in nature, from the seasons of Earth to the lifespans of stars. It invites us to imagine eternity, not as endless silence, but as eternal renewal. For humanity, caught in the briefest flicker of cosmic time, the Big Bounce is a reminder of perspective. Our lives, our civilizations, even our species are transient, but the universe itself may breathe forever. If so, then death and rebirth are not tragedies but inevitabilities, woven into the very fabric of reality. The cosmos, like a living being, inhales and exhales across the ages, each breath a new universe. And so, from the quiet symmetry of cycles, we return once more to uncertainty, for the fate of the universe may not be renewal at all. It may be destruction, violent and absolute, not by collapse, but by expansion itself. If dark energy does not fade but grows stronger, then the future may hold not a bounce but a rip, a universe torn apart by its own acceleration. The universe today is not slowing down in its expansion, it is speeding up. Galaxies are racing away from one another, faster and faster, driven by the mysterious force we call dark energy. This acceleration raises a question as haunting as it is profound. If expansion continues to grow stronger, what will become of the cosmos? One possible answer is the Big Rip, a future where dark energy tears apart galaxies, stars, planets, and even the very fabric of matter itself. In the Big Rip scenario, dark energy does not remain constant. Instead, its strength increases over time. Expansion grows not only faster, but ever more violent, until no force can resist it. Gravity, which binds galaxies together, will fail. The electromagnetic force, which binds atoms, will fail. Even the nuclear forces that hold protons and neutrons together may fail. The universe will not fade into silence, but will be shredded piece by piece in a final act of destruction. The timeline of this fate depends on the nature of dark energy. If it grows, as some models suggest, the end could arrive in 20 to 30 billion years. Long before the final moment, the signs would appear. Galaxies would drift apart so quickly that their light could never reach one another. The night sky would empty as neighbors vanish beyond horizons. Stars within galaxies would no longer remain bound, flung into isolation as their orbits unravel. Planets would be torn from their stars, wandering into the void. As the rip draws closer, destruction accelerates. Billions of years before the end, galaxies dissolve. Millions of years before, stars are ripped apart. Hours before, planets are shredded. In the final fractions of a second, even atoms are torn as the bonds of fundamental forces fail. Space itself stretches so violently that no structure can endure. The universe, once filled with galaxies and stars, ends as a thin, unbound soup of particles and radiation scattered into nothingness. This vision is terrifying in its violence, yet it emerges from equations as naturally as heat death or the Big Crunch. The Big Rip is the logical consequence if dark energy is not constant but dynamic, growing stronger with time. We call this phantom energy, a hypothetical form of dark energy whose density increases as the universe expands. In such a case, expansion feeds on itself. Runaway, and unstoppable, until space-time itself is torn apart. For human beings, this ending is nearly impossible to picture. We think of space as empty, as a stage where events unfold. But in the Big Rip, it is the stage itself that fractures. Space does not remain still while galaxies drift apart. Space stretches so violently that the very relationships between particles are broken. It is not objects moving through space. It is space unmaking the objects themselves. And yet, even in its violence, the Big Rip carries a strange elegance. It shows us that the universe is not bound to one destiny. Its fate depends on the balance between expansion and gravity, between dark energy and matter. If dark energy is constant, the cosmos may end in silence. If it grows stronger, the cosmos may end in fire. The Big Rip is a reminder that the laws of physics are not fully known, that the future of everything hangs on mysteries, yet unsolved. For now, evidence suggests that dark energy behaves like a cosmological constant, unchanging over time. If that is true, the Big Rip may never occur. Expansion will continue, but not to the point of tearing apart atoms. Still, uncertainty remains. Observations are not precise enough to rule out phantom energy. The possibility of a rip lingers, a shadow in the equations, waiting for clarity. To imagine the Big Rip is to confront the fragility of all things. Galaxies, stars, planets, atoms, all the structures we know, depend on forces that may one day be overcome. It is a vision where nothing survives, where the universe itself dissolves. Yet, in contemplating it, we are reminded again of the miracle of the present. For we live in a cosmos that still holds together, still gives rise to light, life, and thought, even as it races toward its uncertain fate. As the Big Rip approaches in this imagined future, the universe becomes a place of escalating tension. Expansion does not remain gentle or gradual. It accelerates beyond comprehension, stretching the fabric of space at a pace that overwhelms the forces that bind matter together. The story of the Rip is not one of slow fading but of increasing violence, a cosmic crescendo that ends in a single catastrophic instant. Long before the final moment, the signs would be clear. Galaxies, once bound collections of stars, would lose their cohesion. The gravitational pull that holds them together would be overcome, and their stars would scatter into the void. The familiar spiral structures, the grand ellipticals, the clusters that span millions of light years, would dissolve. To any observer in this era, the night sky would look strange and empty, as the great cities of the cosmos unravel into scattered islands of lonely stars. On smaller scales, the disintegration continues. Stars within galaxies would no longer remain bound to their centers. Orbits would stretch and shatter as expansion overwhelms gravity. Planetary systems would follow. The Earth, if it still exists by then, would drift away from the Sun, not because of instability in the star, but because the fabric of space itself pulls it apart. The delicate balance of orbital motion would collapse as expansion outpaces gravity's hold. Closer to the final hour, the scale of destruction shrinks dramatically. Stars themselves, those immense furnaces of fusion, would be torn apart. Their plasma would be ripped free as the bonds of gravity can no longer contain them. Planets, moons, and asteroids would be shredded into rubble. The violence does not stop there. Even molecules and atoms, held together by electromagnetic forces, would unravel. Atoms, the building blocks of matter, would split as their electrons are torn from nuclei. Finally, in the last instant, even nuclei would disintegrate, the strong nuclear force overcome by the tearing of space. The sequence is chilling in its inevitability. From galaxies to stars, from planets to atoms, everything unravels step by step, each scale succumbing as expansion grows more violent. In the very last fraction of a second, space-time itself fractures, leaving only a storm of unbound particles and radiation. The universe, once filled with structure and complexity, ends in an instant of chaos and nothingness. The timing of this apocalypse depends entirely on the properties of dark energy. If dark energy is a cosmological constant, the rip will never come. Expansion will continue forever, but its pace will not increase enough to tear matter apart. If dark energy grows stronger, however, then the rip becomes inevitable. Models of phantom energy suggest timelines of tens of billions of years. In some versions, galaxies dissolve a billion years before the end. Solar systems fall apart tens of millions of years before. Planets are destroyed hours before, and atoms themselves are ripped apart in the final heartbeat of the cosmos. For humanity, the Big Rip is both terrifying and strangely liberating. It is terrifying because it offers no refuge. No planet, no star, no black hole could endure. It is liberating because it reminds us that survival on cosmic timescales was never possible. Life exists only in a narrow window between birth and destruction, between the beginning and the end. The value of existence lies not in its permanence, but in its fleeting brilliance. The Big Rip also challenges our intuition about space itself. We think of expansion as galaxies moving apart through emptiness, but in truth, it is space itself that expands. In the Rip, expansion becomes so powerful that space is not a background, but the very engine of destruction. It is not objects moving away from each other. It is the fabric of the cosmos, tearing apart the objects themselves. And yet, for all its violence, the Big Rip is not chaos. It is the outcome of precise equations, of the balance between dark energy and matter. If the numbers tip one way, the universe drifts into silence. If they tip another, the universe ends in shreds. Both fates are written into the laws of physics, waiting only for the true nature of dark energy to be revealed. As we look to the future, the Big Rip stands alongside heat death and the Big Crunch as one of the great possible endings. It is a reminder that the destiny of the cosmos is not yet certain, and that our understanding of dark energy will decide which vision prevails. Until then, Rip remains a haunting possibility, a cosmic nightmare woven from the unknown. As the Big Rip draws to its conclusion, the universe transforms into a theater of accelerating collapse, though collapse here is not inward, but outward. The very expansion of space, once gentle and steady, becomes violent and irresistible. Every scale of structure, from the vastest galaxy clusters to the tiniest atomic bonds, falls victim to the growing strength of dark energy. Billions of years before the final instant, galaxies dissolve, their stars cast adrift into an expanding void. Millions of years before, solar systems fail, their planets torn from orbit. Days before, stars themselves unravel, unable to hold their plasma together. Seconds before, molecules split, then atoms, then nuclei. In the final heartbeat, nothing remains but scattered particles, flung apart as the stage of space-time itself rips into pieces. The Rip is unlike any other ending we have imagined. Heat death offers silence, the Big Crunch offers fire, the bounce offers renewal, but the Rip is annihilation by expansion itself. It is the destruction not of objects within space, but of space itself, pulling everything apart until there is no togetherness left. What makes it haunting is its inevitability once the conditions are met. If dark energy strengthens with time, then no force in the universe can resist it. This ending depends on a single unknown: dark energy. We do not yet know its true nature. Observations suggest it behaves like a cosmological constant, unchanging over time, which would mean no Rip. But uncertainties remain. If dark energy is phantom energy, if it grows stronger as the universe expands, then the Rip is written into the equations. The difference between silence and shredding lies in the behavior of something we cannot yet explain. For humanity, the Big Rip is both terrifying and strangely clarifying. Terrifying because it offers no escape. Clarifying because it reminds us that permanence was never the point. The universe is not a static monument, but a dynamic story. Galaxies, stars, planets, life itself, all are temporary forms carved from the laws of physics. To imagine the Rip is to face that truth in its starkest form. And yet, there is wonder even here. The idea that space-time itself can destroy matter shows us how deeply mysterious the universe remains. Expansion is not an empty drifting, but an active force, shaping the fate of all things. To live in an accelerating universe is to live in suspense, uncertain of which ending awaits. Thus the Big Rip joins the catalogue of cosmic fates, silence, collapse, renewal, annihilation. Each scenario flows from the same laws of physics, each consistent with what we know, each dependent on what we do not yet know. The future of everything hangs on the nature of dark energy, the most mysterious force in the cosmos. Until we unravel that secret, all endings remain possible. But the rip is not the only exotic possibility. Beyond gravity, beyond expansion, beyond entropy, lie stranger ends still. Quantum instability, vacuum decay, or collisions with other universes may hold fates even more shocking. If the Big Rip is violent, these alternatives are absolute. To explore them is to step beyond the boundaries of known physics into the shadows where speculation begins. The endings we have traced so far: heat death, the Big Crunch, the Big Bounce, the Big Rip, all emerge from the familiar forces of gravity, thermodynamics, and cosmic expansion. They are written into the known framework of physics, extrapolated across unimaginable spans of time. Yet, the universe may not wait that long. Beyond the certainties of stars and black holes, beyond the pull of gravity and the push of dark energy, lie stranger possibilities. These are the exotic ends, born not of inevitability, of quantum chance, hidden fields, and the mysteries of the multiverse. Among these possibilities, vacuum decay stands as one of the most startling. The fabric of reality itself may not be perfectly stable. Our universe is built upon a vacuum state, the lowest possible energy configuration of quantum fields. But what if this state is only metastable, a false minimum perched above a deeper valley? If so, a sudden quantum event could trigger a transition to the true vacuum. A bubble of lower energy would form and expand at nearly the speed of light, rewriting the laws of physics as it spread. Within the bubble, the constants of nature could shift, atoms could no longer hold together, and all structures would vanish in an instant. There would be no warning, no resistance, only transformation as space-time itself was remade. The idea of vacuum decay is not wild speculation, but a real consequence of quantum field theory. Calculations of the Higgs field, discovered in 2012, suggest that our universe may be precariously balanced between stability and decay. If true, then the cosmos lives on borrowed time, a fragile state that could collapse at any moment. Yet the timescales are immense, far beyond the age of the universe so far. Still, the possibility remains. The end could come not from the exhaustion of stars or the pull of gravity, but from the quantum instability of the vacuum itself. Even stranger are the possibilities of phase transitions in fields we do not yet know. Just as water can shift from liquid to solid to vapor, quantum fields may undergo transitions that reshape the universe. In its earliest moments, the cosmos likely passed through several such phases, symmetry-breaking events that gave rise to forces and particles. Another transition could occur in the future, altering the structure of matter, energy, and even space-time itself. The universe we know could dissolve into something unrecognizable, a new physics sweeping across the cosmos. Beyond even this lies the possibility of collisions between universes. If our cosmos is part of a multiverse, a vast collection of universes, each with its own laws, then collisions are possible. Universes could brush against one another, their boundaries overlapping, their physics colliding. The effects could be catastrophic, erasing the structures of one universe, or merging them into something new. The evidence for a multiverse is uncertain, drawn from speculative models of inflation and string theory. But if true, it expands the horizon of endings, far beyond what we can now imagine. These exotic ends are frightening because they are sudden. Heat death and the Big Crunch unfold over trillions of years, giving time for the universe to fade gracefully. Vacuum decay, phase transitions, and multiverse collisions could arrive without warning. One moment, the cosmos as we know it. The next, nothing familiar remains. They remind us that the stability of our world is not guaranteed, that the ground of reality itself may shift. Yet even here there is wonder. These possibilities show us that the universe is larger, stranger, and more fragile than we ever believed. They reveal that the cosmos is not a static backdrop but a dynamic field of possibilities where existence itself is contingent. To contemplate these endings is not only to face mortality on a cosmic scale, but also to glimpse the depth of mystery that still surrounds the universe. The exotic ends are not certainties, they are possibilities, shadows cast by theories not yet confirmed, but they teach us humility. We cannot assume that the cosmos will fade gently. It may vanish suddenly, transformed by forces we barely understand. To live in such a universe is to live in uncertainty, but also in awe. And so we arrive at a crossroads. The universe may end in silence, in fire, in renewal, in shredding, or in transformation. To know which awaits us, we must seek signs, evidence hidden in the light of galaxies, the echoes of the Big Bang, and the behavior of expansion itself. The fate of the cosmos is not beyond reach. It lies in the data we gather, clues we read from the stars. As we extend deeper into the strange landscape of exotic endings, the possibilities only grow more unsettling. Vacuum decay may strike without warning, but it is not alone. Other theoretical ends emerge from the frontiers of physics, each one suggesting that the stability of our universe is more fragile than it appears. One such possibility is a new phase transition in fields we have not yet fully mapped. In the earliest moments after the Big Bang, the universe underwent several transitions as fundamental symmetries broke, releasing forces and particles. These changes were violent, reshaping the very rules of physics. There is no reason to assume that all such transitions are behind us. If the underlying fields of reality shift again, the constants of nature may change. What holds matter together now could fail. Atoms, chemistry, even the possibility of stable structures could vanish in an instant. The universe would still exist, but it would not be recognizable. Another exotic end comes from the idea of higher dimensions and multiverses. If our cosmos is not alone, but part of a larger multiverse, then interactions between universes become possible. Two universes could collide, their boundaries merging, their energies unleashing catastrophes beyond imagination. In some versions of string theory, universes exist as membranes floating in higher dimensions. Collisions between these branes could produce events like the Big Bang itself. If so, another collision in the future could erase the universe we know, replacing it with something utterly new. Even more speculative is the idea that exotic particles or unknown forces could destabilize the cosmos. Physics beyond the standard model hints at possibilities we cannot yet confirm. Dark matter, which makes up most of the matter in the universe, remains a mystery. Dark energy, driving acceleration, is even less understood. If their natures shift, the structure of the cosmos may collapse in ways we cannot now predict. It is humbling to realize that the ultimate fate of everything may hinge on forces we do not yet comprehend. What unites these exotic ends is their suddenness. Heat death, the crunch, the bounce, even the rip unfold over billions or trillions of years, giving time for stars to fade and galaxies to drift. Vacuum decay, phase transitions, and multiverse collisions could happen at any moment. There would be no warning, no sign, no escape. One moment, the universe as we know it. The next, everything transformed or annihilated. These possibilities are unsettling, but they also reveal a profound truth. The universe is not a finished stage upon which events unfold. It is dynamic, alive with potential, shaped by forces we barely understand. The stability of reality itself is a question, and the end may come not from exhaustion, but from transformation. For us, contemplating these exotic ends is not about prediction, but about perspective. They remind us that the cosmos is stranger than we know, that existence is fragile, and that the rules we take for granted may one day change. To live in such a universe is to live with awe, to recognize that reality is both gift and mystery. But speculation alone is not enough. To decide which fate awaits us, we must search for evidence. The answers may be written in the light of distant galaxies, in the afterglow of the Big Bang, in the behavior of cosmic expansion. The end of the universe is not beyond our reach. It is a question that science itself is now daring to ask. As we follow the trail of exotic endings to its conclusion, we encounter scenarios that blur the line between science and imagination, yet remain rooted in the possibilities of physics. Each one reminds us that the stability of the cosmos cannot be taken for granted, and that what feels eternal may be temporary on scales beyond comprehension. Consider again the possibility of vacuum decay. In this ending, the laws of nature themselves are rewritten. The constants we know, the strength of electromagnetism, the ratios that allow chemistry to exist, the balances that permit stars to shine, all could change in an instant. Within the expanding bubble of true vacuum, atoms would fall apart, light would propagate differently, and time itself might take on a new character. The bubble would expand at nearly the speed of light, leaving no chance for escape or resistance. For those within the old vacuum, the end would arrive without warning, swift and absolute. Or imagine a phase transition in a field we do not yet know. The early universe already underwent such transitions, each one sculpting the cosmos into what we see today. If another occurred, the transformation could be equally radical. Structures could dissolve, particles could change, even the dimensionality of space-time might shift. In such a case, the universe would not simply end. It would change into something unrecognizable, continuing in a form that bears no resemblance to what came before. Then there is the possibility of the multiverse. If our cosmos is only one bubble among many in a vast cosmic foam, collisions are inevitable. Perhaps some leave subtle imprints, circular scars in the cosmic microwave background. Perhaps others are catastrophic, tearing universes apart or merging them into new forms. To live in such a reality is to accept that our universe is not unique and that its fate may not be entirely in its own hands. A collision with another universe could arrive without warning, rewriting space-time itself. All of these scenarios share a disquieting feature. They are sudden. Unlike the slow fade of heat death or the long collapse of a crunch, exotic ends offer no time for preparation, no final moments of reflection. They come like lightning, rewriting everything in an instant. In that sense, they are the most humbling of all. They remind us that our sense of permanence rests on assumptions about stability that may not hold forever. And yet, even here, there is wonder. These endings show us that the universe is not a static machine, but a living mystery. Its laws may shift, its fabric may transform, its story may contain twists we cannot predict. To contemplate such ends is not to despair, but to marvel at the depth of the unknown. We live in a cosmos where even the end is uncertain, where the future holds not just inevitabilities, but possibilities beyond imagination. Thus the catalogue of endings expands. Silence in heat, death, collapse in the crunch, renewal in the bounce, annihilation in the rip, transformation in exotic ends. Each one flows from physics, from the interplay of forces and fields, from the mysteries of dark energy and quantum mechanics. Which one awaits us is not decided. The answer lies in evidence, in the data we gather from the stars, the galaxies, and the afterglow of the Big Bang. And so we turn from speculation to observation. To know how the universe will end, we must search the cosmos itself for signs. The answers are out there, written in the light that has traveled billions of years, waiting to be read. The fate of everything may yet be revealed by what we discover. To imagine the many endings of the universe is to confront possibility. To decide among them is the work of observation. For all the grandeur of theory, it is evidence that tells us which future awaits. The stars, the galaxies, the radiation left over from the first fire. These are not only relics of the past, but guides to the future. By measuring the cosmos with increasing precision, we hope to read its destiny written across time. The first and most vital clue lies in the expansion of the universe itself. In the 1920s, Edwin Hubble discovered that galaxies are rushing away from us, their light stretched to longer wavelengths. This was the first proof that the universe is expanding. Since then, astronomers have worked to measure the exact rate of this expansion, a value known as the Hubble constant. Yet here lies a puzzle. Different methods of measuring the expansion give different answers. Observations of the early universe, using the cosmic microwave background, suggest one value. Observations of nearby galaxies and supernovae suggest another, higher value. This tension, known as the Hubble tension, may point to errors in our measurements, or it may be the first sign of new physics that reshapes our understanding of cosmic fate. Supernova surveys have been central to this effort. Type 1, a supernovae, exploding stars of uniform brightness, act as cosmic mileposts. By comparing their apparent brightness to their true brightness, astronomers can calculate distances. In the 1990s, teams studying these supernovae discovered that distant galaxies are not just receding but accelerating. This was the shocking discovery of dark energy, the invisible force that now dominates the dynamics of the cosmos. It was this revelation that first suggested endings like the heat death or the Big Rip, futures driven not by gravity but by acceleration. The cosmic microwave background offers another window. This faint afterglow of the Big Bang carries information about the universe when it was only 380,000 years old. Tiny fluctuations in its temperature map the seeds of galaxies, while its overall spectrum reveals the balance of matter, radiation, and dark energy. By comparing these measurements to models, cosmologists can predict the long-term behavior of expansion. If dark energy is truly constant, the universe will drift into heat death. If it changes, other endings become possible. Other signs may lie in the distribution of galaxies themselves. Large-scale surveys, mapping millions of galaxies across billions of light years, trace the cosmic web. The filaments and voids of this structure hold clues to how matter clumped over time and to how expansion shaped that growth. By studying this web, astronomers can refine their measurements of dark energy, narrowing the possibilities for the fate of the cosmos. These efforts require extraordinary precision. To decide whether the universe ends in silence or in fire, we must measure its expansion rate to fractions of a percent. To know whether dark energy is constant or changing, we must watch galaxies across billions of years of light travel. Each observation adds another piece to the puzzle, bringing us closer to the answer. And yet, the more we learn, the stranger the picture becomes. The Hubble tension persists, defying resolution. The nature of dark energy remains unknown, a name for a mystery rather than an explanation. Even gravity itself may not be fully understood at cosmic scales. Each question we answer raises new ones, reminding us that the future of the universe is still uncertain. For humanity, this search is more than scientific. It is existential. To know how the cosmos ends is to know something of our place within it. Will everything fade into silence, collapse into fire, renew in cycles, or tear apart? The answer lies not in speculation, but in the light of galaxies and the afterglow of the Big Bang. The universe is telling us its story. We need only learn how to listen. The effort to read the universe's fate continues through a variety of measurements, each probing different aspects of cosmic history. Supernovae remain among the most powerful tools, acting as beacons across billions of light years. By comparing their distances to the rate at which galaxies recede, astronomers build a timeline of expansion. The discovery that this expansion is accelerating was a shock, but the details of how acceleration behaves remain uncertain. Are we seeing a perfectly steady push, like a constant wind, or something more variable, like a storm whose strength shifts over time? The difference could determine whether the cosmos drifts gently into heat death or is ripped apart in a violent end. Baryon acoustic oscillations provide another way to measure expansion. In the early universe, sound waves rippled through the plasma of matter and radiation, leaving imprints on the distribution of galaxies. These ripples act as a cosmic ruler, a standard measure against which distances can be checked. By mapping galaxies in immense surveys, astronomers trace these oscillations and refine their calculations of the Hubble constant and dark energy's influence. The more precise the map, the better we can predict the universe's trajectory. Another key comes from gravitational lensing, the bending of light by mass. Massive objects like galaxy clusters distort the light from background galaxies, stretching and magnifying them into arcs and halos. By measuring this lensing effect across millions of galaxies, scientists can trace the distribution of dark matter, the hidden scaffolding of the cosmos. This in turn reveals how structures grow under the competing influences of gravity and expansion. If expansion suppresses structure more than expected, it may hint that dark energy evolves over time. The study of the cosmic microwave background continues to refine our picture. Its polarization patterns and subtle variations carry information about the very first moments of the universe. Some theories predict that exotic features, such as evidence of collisions with other universes or imprints of primordial gravitational waves, may be encoded in this radiation. If such signatures were found, they could reshape our understanding of beginnings and endings alike, pointing to cycles, multiverses, or other exotic possibilities. In recent years, new methods have joined the search. Fast radio bursts, brief flashes of radio energy from distant galaxies, may serve as probes of cosmic expansion. Standard sirens, the gravitational wave signals from colliding black holes or neutron stars, provide an independent way to measure distances and expansion without relying on light. Each new method adds another layer of data, another chance to resolve the mysteries of dark energy and the ultimate fate of the cosmos. The challenge is that these measurements often disagree. The Hubble tension, the gap between expansion rates measured from the early universe and those from the nearby universe, has not gone away. If it is not a mistake in our observations, it may be a sign that our models are incomplete. Perhaps new physics is at work, a hidden factor influencing expansion in ways we have not yet accounted for. If so, the future may hold endings we have not yet imagined. For now, the evidence points toward a universe dominated by dark energy, with expansion continuing indefinitely, but uncertainty remains. Small shifts in the data could mean the difference between a slow drift into silence and a violent tearing apart. The stakes are cosmic. By refining our observations, we do not simply learn numbers, we learn the destiny of everything. It is a humbling task. To measure the expansion of the universe is to read the story of billions of galaxies across billions of years. To trace its fate is to predict the end of time itself. Yet this is the work of science, turning questions of philosophy into matters of evidence, transforming speculation into knowledge. The universe is vast, but it is not beyond our reach. In its light, it tells us how it began and where it is going. We need only look closely enough to hear its voice. The search for signs of the universe's end is not only a question of physics, but also of patience. The cosmos reveals its secrets slowly, through light that has traveled for billions of years, through subtle ripples imprinted on radiation, through the faint bending of distant galaxies. Each clue is precious, and each one brings us closer to understanding which of the possible endings awaits. One frontier lies in the careful study of dark energy itself. At present, we know little beyond its effect. It accelerates the expansion of space. Whether it is a cosmological constant, a field that changes with time, or something more exotic is unknown. To probe it, astronomers measure the expansion rate across different epochs, mapping how galaxies move and how structures form. If dark energy is constant, then heat death looms as the likely fate. If it grows stronger, the Big Rip becomes possible. If it weakens or reverses, contraction could one day begin, leading toward a crunch or bounce. The destiny of the universe is tied to the behavior of this one mysterious component. The cosmic microwave background continues to be one of the richest sources of data. Missions like COBE, WMAP, and Planck have transformed our understanding, measuring temperature fluctuations with extraordinary precision. These fluctuations reveal the conditions of the early universe, the density of matter and energy, and the geometry of space itself. Future missions aim to detect even fainter signals, such as the imprint of primordial gravitational waves. Such a discovery would shed light not only on the birth of the cosmos, but also on whether our universe might be one of many in a broader multiverse. Closer to home, Surveys of galaxies stretch ever further into the sky. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies, tracing the cosmic web across immense distances. New instruments, like the Vera C. Rubin Observatory, promise to multiply this data, capturing the motions and positions of billions of galaxies. With such maps, scientists can test whether the laws of gravity themselves hold true on the largest scales. If they do not, new physics may await, altering our vision of the end. Even gravitational waves, ripples in space-time first detected in 2015, are becoming tools of cosmology. As detectors grow more sensitive, they will capture signals from more distant events, turning black hole mergers and neutron star collisions into standard sirens for measuring cosmic expansion. These signals, independent of light, provide a fresh way to resolve the tension in the Hubble constant. Each new detection sharpens our picture of the future, but the more we learn, the more elusive certainty becomes. The Hubble tension remains unresolved. Dark energy defies explanation. The distribution of galaxies sometimes suggests discrepancies with our models. Each anomaly could be an error, or it could be a clue to deeper truths. Perhaps the universe harbors physics we have not yet glimpsed, laws that will rewrite our understanding of its fate. What is clear is that we live in a moment of extraordinary discovery. For most of human history, the end of the universe was a matter of myth and speculation. Today, it is a scientific question, pursued with telescopes, satellites, and equations. We may not yet know whether the cosmos ends in silence, fire, renewal, or sudden transformation, but we are closer than ever to finding out. And as we look forward, we find that each answer deepens the mystery. The more precisely we measure, the stranger the universe appears. Perhaps this is inevitable. The cosmos is not obliged to conform to our expectations. It may hold endings we have not yet imagined, but whatever the truth, it is written in the light of the stars, waiting for us to read it. Thus, from the search for signs, we turn to reflection. For beyond the data lies a question, not of physics, but of meaning. What does it matter if the universe ends? What place does such knowledge hold in our brief lives? To confront the end is to confront our own impermanence, but also to recognize the wonder of existing at all. We have walked through visions of silence and fire, of collapse and renewal, of shredding and sudden transformation. Each possibility emerges from the laws of physics, extended to their ultimate consequences. Heat death, the big crunch, the big bounce, the big rip, vacuum, decay, and other exotic ends all stand as potential fates of the cosmos. To hold them in mind at once is to see the universe not as eternal but as fragile, shaped by forces that will one day undo all things. Yet as we contemplate these endings, we must also ask what they mean for us. Creatures who live for only a brief instant in cosmic time. The inevitability of an ending does not diminish the present. In fact, it heightens it. Just as the finite span of a human life gives each moment its weight, so too does the finite span of the cosmos make its existence precious. Stars shine because their fuel will run out. Planets host life because their conditions will change. Civilizations rise and fall because time moves forward. The impermanence of all things is not a flaw, but a feature, a reminder that existence is dynamic, ever-changing, and always precious. To imagine the end is also to recognize the power of science. For the first time in history, humanity can look beyond myth and speculation, to evidence, to equations, to data gathered from the sky itself. We can trace the expansion of galaxies, measure the afterglow of the Big Bang, detect the ripples of gravitational waves, and from them build scenarios of the far future. We may not yet know which ending awaits, but we know the possibilities. We know that the universe is not infinite in its forms, that its destiny is tied to its structure, that its story is written in the laws of physics. But there is also humility here, for each answer opens new questions. Dark energy remains mysterious. Gravity itself may not be fully understood, and the nature of the vacuum could conceal deeper truths. The end of the universe may not be one of the endings we have imagined. It may be stranger still, beyond the grasp of our current theories. To reflect on the end is to reflect on the limits of knowledge and on the endless drive to push those limits further. For humanity, the end of the universe lies far beyond our reach in time. Whether it comes in tens of billions of years or in sudden quantum catastrophe, it will not come within the span of human history. Yet it matters that we think about it. To ponder the end is to place our lives in perspective, to see our struggles and triumphs against the backdrop of eternity. It is to realize that our existence is both infinitesimal and extraordinary, a brief flicker of consciousness in a cosmos vast and fleeting. And so we ask, does it matter if the universe ends? In one sense, no, for we will be gone long before. In another sense, yes, profoundly, for the knowledge itself enriches our experience. To know that all things end is to live with greater urgency, to cherish the present, to see wonder in the ordinary. The universe will not end with our permission, but with the silent unfolding of its laws. Yet while it lasts, it gives us the chance to wonder, and in that wonder lies meaning. The reflections deepen when we step back and see how each possible ending mirrors something within our own experience. Heat death resembles the quiet fading of life, where energy is spent and silence takes hold. The Big Crunch mirrors the inevitability of return, everything drawn back to origin. The Big Bounce echoes renewal, the idea that destruction carries the seeds of creation. The Big Rip resembles disintegration, when bonds once thought unbreakable dissolve. Vacuum decay reminds us that stability may be an illusion, that what feels secure may change without warning. Each cosmic ending is both a scientific hypothesis and a metaphor for the impermanence of all things. There is something profoundly human in this search. We ask not only how the universe began, but also how it will end, because beginnings and endings shape how we understand meaning. Myths once told of cycles of death and rebirth, of eternal returns, of gods who create and destroy. Today we tell the story with equations and telescopes, but the impulse is the same. To ask how the cosmos ends is to place ourselves within its story, to understand our fleeting existence against a background that is vast and incomprehensible. What emerges from this reflection is not despair, but wonder. If the universe drifts into silence, then every spark of life is a defiance of entropy, a brief but brilliant interruption in the march toward disorder. If the universe collapses, then every star and every galaxy is part of a grand cycle that may begin again. If the universe bounces, then our cosmos is one of many, each born from the ashes of the last. If the universe rips apart, then existence itself is fragile, a miracle suspended on the balance of unseen forces. If the vacuum decays, then reality is contingent, precarious, and endlessly mysterious. In every ending, there is awe. Philosophy meets science here. The end of the universe may feel remote, but it forces us to ask what permanence means, what value means, what purpose means in a cosmos where nothing lasts. The answer cannot be permanence, for permanence does not exist. The answer must be presence, the awareness of the moment, the recognition that meaning arises not from eternity, but from the brief brilliance of existence. In this way, to reflect on the end is to reflect on life itself. Both are finite, both are fragile, both are extraordinary. The same laws that will one day unmake galaxies are the laws that now allow stars to shine and life to emerge. The end is not separate from the present, but woven into it. The final chapter of the same story that allows us to exist at all. And so we find ourselves not diminished, but enlarged. To contemplate the death of the universe is not to fall into despair, but to be reminded of wonder. We are the universe looking at itself, briefly conscious of its own destiny. That is meaning enough. The reflection continues when we consider the final piece of this journey, the closing meditation on the fate of all things. We have walked through the mechanics of endings, traced their mathematics, and followed their timelines across unimaginable spans. Yet the final chapter does not rest in equations alone. It rests in the recognition of what it means to be here, now, aware, in a universe that will one day end. When we say the universe will end, we do not mean it will end with our permission. It will not consult us, nor will it notice our presence. It will unfold according to its laws, as it has since the first burst of light. Heat death will not ask if we are ready. A crunch will not wait for witnesses. A bounce will not require participants. A rip or a decay will not pause to consider the fragile miracle of life. The universe ends because that is what universes do. Yet the miracle lies not in avoiding the end, but in existing at all between beginning and ending. This is the lesson written into the cosmos. Impermanence is not a flaw, but the essence of existence. Stars shine because they exhaust their fuel. Galaxies form because gravity gathers matter in temporary webs. Life arises because conditions hold for a time before they change. Consciousness emerges because the universe allows complexity, even if only briefly. To reflect on the end is to see that the value of existence lies not in permanence but in presence. There is a quiet beauty in this. The cosmos does not promise eternity, but it does offer wonder. It offers skies filled with galaxies, atoms that dance into chemistry, a world where life can arise and ask questions. It offers us the chance to know, to feel awe, to reflect. If the universe will one day be silent, then all the more reason to listen to it now. If it will one day be empty, then all the more reason to cherish its fullness. If it will one day be gone, then all the more reason to marvel that it is here. In the end, the cosmos will not close its story with fanfare. It will simply unfold. Heat death, crunch, bounce, rip, decay, or something beyond whatever comes. It will come without drama, without care for our presence. But within the vast indifference of the universe lies the miracle of our awareness. We are the eyes through which the universe sees itself, the mind through which it contemplates its fate. That, perhaps, is meaning enough. The universe will end, not with our permission, but with the silent unfolding of its laws. Yet while it lasts, it gives us the chance to wonder. And in that wonder, we find not despair, but a reason to live, to learn, and to gaze into the dark with awe.